Alright, hell yeah. So we have linear algebra, and I never do this, you know what I mean? Just do like a 2-hour video and then just do the problem in 5 minutes. So what we have going on is eigenvalues and eigenvectors. Now I'm going to do this whole thing without even saying ever the word eigen at all. So we have matrix A times vector u is going to be equal to a scalar times that same vector. And so the proof of this, or to do some sort of manipulation for solutions, is to get this, because this side is a matrix, I want this side to be a matrix. So I'm going to take this scalar, multiply it by an identity matrix that's the same size as matrix A. Here's matrix A for this problem. Now what I can do is subtract both sides by this value, you know what I mean? Just get this to the other side by just subtracting it. And then I'm left with the 0 vector over here. And I can factor out the matrix portion. I have a matrix times a vector minus a matrix times a vector. The same vector, so the vector factors out. Now this portion is just a matrix. I put it in brackets just to say, hey, once you do the subtraction operation and this scalar times the identity, you're just left with a single matrix. And so we have it in the form of AX is equal to B. Cool. Now, because this is the 0 matrix, hell yeah, almost stumbled there. It's very similar to saying like something multiplied by something is 0. Well, if this something is 0, cool, it's all a good solution. If this something is, if this matrix actually just turns out to be 0, just zeros in all of its matrix-y locations, then hell yeah, it'll work out. Anyway, so we have the general solution is x, y is equal to 0. And that would look like this. Just this matrix U is going to be in the form of x and y. And then if U is 0, then U is the 0 vector. The 0 vector is just zeros in that xy position. Okay. And then we're going to find out that if, well, and it's not even as if this side just has zeros in it, there's a solution. This side will have a solution, where x and y, are some number. If this matrix is linearly dependent. So if this matrix is linearly dependent, then we have an infinite number of solutions. And the test for linearly independence or dependence is taking the determinant of this matrix. And we're just going to say if it's 0. We're going to assume that it's 0, and if it is 0, then we're going to have an infinite number of solutions. And then we can, and then we'll just go from there. Hell yeah. But up to this point in the book, what we've been doing is having something that's AX is equals to B. And if we do have this in just a general form, maybe I want to take the inverse. And if I'm able to, hell yeah, I want to take the inverse of both sides. That would look like this. Because I took the inverse of both sides, this becomes the identity matrix, kind of just goes away. So then I'm just left with the solution is going to be the inverse of matrix A times just B. Hell yeah. And that's going to give us the values. But here's the kicker. The definition of an inverse is 1 divided by the determinant of that matrix divided by the cofactor transformed of that matrix. But if the determinant of that matrix is 0, we're going to be dividing by 0, and we can't use this approach. But for this video, we are. You will get infinity. So what we're going to do is just slightly modify our matrix just so the determinant is a smaller value. And then this side we're going to slightly modify so it's not 0, 0. Maybe it's like 0.1, 0.1. So hell yeah. And now what we're going to do is we first need to set the determinant equal to 0 to get the values of this scalar that satisfy. Hell yeah. I was just like, satisfy what? What the hell are we even talking about? Well, we're trying to actually find multiple solutions. That is our goal. We're going to say, hey, there is a, if x and y are 0, this is going to be 0. But we want to assume an infinite number of solutions. And the only way to do that is if this determinant is 0. And we can play around with this scalar, so we're going to find a value for that scalar that makes this determinant 0. And this is simply just plugging a into here, the identity, and then the scalar. So that's what we have right here. We have the identity. So that portion, you know what I mean, of this process is like, cool, we got down to here where we can find solutions for this vector. Again, we have a common solution when this side is 0, 0. It's very similar to having a product of two things equal 0. If this product is 0, then it's 0. If this product is 0, it's 0. If they're both 0, cool, it's extra 0. You know what I mean? But if one is 0, the other could be any number. So that's what we're saying. We're going to say, hey, if, oh yeah, that's kind of interesting. Holy hell, this is so cool. I didn't even realize you know what I mean? Like when you do proofs, you're just like, okay, we're moving things around, and it's just like, okay, we're going to get a solution where we have this matrix over here as like 2, 0, 1, 3 times our, you know what I mean, our vector. Cool. And then, and that's what we're going to say. And we're going to say that's equal to our scalar times that vector. But we just said we can factor out that vector, where if we have the matrix minus this scalar times the identity, you know what I mean? So that is 0. I didn't realize that. You know what I mean? There's a lot of hand waving, it feels like, but no. Like literally, our solution will make this matrix A minus our scalar times the identity. That portion will be 0. So that is kind of fascinating. This is difficult to solve. We don't know how. I think that's the issue. It's just like we don't know. Let's see. No, I'm so glad I'm doing that part because I don't think that's true at all. I think matrix A minus this scalar times the identity does not have to be equal to 0. You know, you're not just going to get zeros everywhere in this matrix because you're going to multiply by a solution or an infinite number of solutions. You're going to have number in the x, y that actually make that 0. And when you do matrix multiplication, you're doing like, hey, one value times the other value. Maybe plus one value times a negative value. And those are going to cancel out. So you can still get a solution. You know what I mean? So yeah, so that was a faux pas. But yeah, this is fast. I thought this was going to be the fastest way, but I'm still like just picking up like cool stuff. But anyway, we'll try to do this as fast as possible, and then you can kind of just see the grind that I've been doing through this process. Alright, so the main kicker for this proof is just the fact that the determinant of this matrix is 0. So that is the first part that we're going to be starting on. And then what is this? So we have A, which is just 2, 0, 1, 3, minus the scalar. And see how I'm not saying this is the eigenvalue. I said I wasn't going to say it, but that's the eigenvalue. The eigenvector is u. Once we solve for u, and it's in the form of this, which we'll get to in a second, that is the eigenvector. Like, yeah, so eigenvalue, eigenvector. Anyway, back to never using those again. Until we have like a deeper understanding, I just don't see the benefit of chiming out some guy's name. Like, even for students learning about pi, you should just say 3, you know what I mean, then 3.1, you know what I mean, once you graduate 5th grade, 3.14. I don't know how you're going to do it, but yeah, using complex labels on physics and math, I think is a detriment to physics and math. Hell yeah, it's barriers for, you know, new people getting into it. Even me, it's just like, I don't even want to say the word eigenvalue. It's a lot of syllables, and it's a lot of funny sounding, you know, things. Anyway, hell yeah, what are we doing? The determinant of this is equal to 0, so we have matrix A minus the scalar times the identity. So we're just going to multiply the scalar through, so we're going to have, you know what I mean, the scalar 0, 0 scalar. And when we do the subtraction, 2 minus the scalar, that's hell yeah. And then 0 minus 0, 1 minus 0, 3 minus the scalar, because we multiplied it through. A scalar gets multiplied in every location. We just have 0 times the scalar, so those are just 0. And then the determinant of a 2 by 2 matrix is this value multiplied by that value, subtract this value multiplied by that value. So that's going to be 0, but we do have 2 minus the scalar times 3 minus the scalar. And this Greek symbol is lambda. I'm not going to use that either anymore. But yeah, not using eigenvalues eigenvectors or the term lambda, because I think even Greek letters sound like it's going to be difficult. Booyah. All right, so what satisfies this equation when the scalar is 2 or the scalar is 3? We're good to go. This equation is satisfied. So we're going to get two different solutions. I'm just walking us through when the scalar is 2. Hell yeah. And then and I'm going to do it in this unique way of saying, we had this, from our proof, we had, we got down to this part. This matrix times our solution vector is equal to 0. And that, if this scalar is 2, I'm going to plug this into our matrix as just that. We took the determinant of the matrix, but that matrix is just, so we're going to do 2 minus 2 is 0, 0, 1, and then 3 minus 2 is 1. So that is our matrix. So in this proof process, we now have our matrix. It's 0, 0, 1, 1 times u times the 0 matrix. Hell yeah. And now, I don't like doing Gaussian elimination on linearly dependent stuff because it gets confusing. So I think this is a cool method if you're like, I trip up on this all the time. So what we're going to do is we know that the determinant of this is 0, as we said it is. So what we're going to do is we're going to make sure the determinant is just increased by 0.1. That's going to be our factor of increase. Our change is going to be 0.1. It could be 0.01, and you'll see that we can get a more accurate answer if we do that. Only change one of the values to make it that increment. Because determinant's a multiplication of two things, we're just going to do So in this, we're going to do 0.1 times 1 is 0.1 minus 0. So hell yeah. So that's our new determinant. And because this matrix now has a determinant, we can take the inverse of it. The inverse of a matrix is 1. Do I even have that written anywhere? The inverse of a matrix is 1 divided by the determinant of that matrix times the cofactor transformed. Now I'm trying to bust this out. So anyway, so we have the determinant's 0.1. 1 divided by that is 10. So we got that part. The cofactor transformed is the cofactor, with a diagonal switch. If it's on this diagonal, there's no switch. If it's over there, it gets switched to there. So yeah, so we're going to take, so this is our matrix. We're going to take the cofactor transformed of it, which is pick a location and find the minor and see if it has a sign change. If it has a sign change, that's the cofactor. The sign change at this location is, there's no sign change at this location and that location. Watch the video, we go over that proof. But anyway, let's just bust this out. So we have, and this is probably the hardest part, the minor of this location, cross out column and row. The minor, and the minor is do that. Cross out column and row of the value you're taking it and find the determinant of the remainder. The determinant of a single matrix number is just that number. So the minor at that location is 1, booyah. The minor at this location is 0.1, booyah. The minor at this location is 1, but we're going to have a sign change, and it's going to be transposed. They all had a sign change and transposed, but the diagonal doesn't transpose because it flips on that diagonal. The diagonal doesn't have a sign change because of the definition of the cofactor. And so only this will be a -1 right there, and then the minor at that location will be 0. -0 flipped, and so that's what we have. So hell yeah. So now we have our inverse, and then I was just showing you that if we have our inverse, the solution is just the inverse times matrix B. Now matrix B is 0, and we have to bump matrix B just by a little bit. So we're going to bump matrix B by that same value we chose, 0.1. And so now matrix B is now 0.1, 0.1. So now we have the solution vector, which is u, is going to be the inverse of A times, kind of our, the inverse of, our funky equation that we just boosted a little bit, multiplied by our 0 vector that we boosted a little bit. So hell yeah. So we're going to have, this is going to multiply 10 through, 10, -10, and 1, and then 0. And then, ooh, I did this. There's got to be a 1 there. There you go. So let's see if this works. So we have 10 times 0.1 and plus 0. So that's going to be 1. We have negative 10. This is going to be negative 0.1. Sorry. Negative 10 times 0.1 is negative 1, plus 1 times 0.1, which is just 0.1. So we have negative 1 plus 0.1, that's negative 0.9. Hell yeah. And then in the video, I show that if we boost this to 0.0, or I mean kind of reduce that, try to make it closer to 0, like just a smaller change, this is going to be negative 0.99. And so now we're basically at the end of the video, where this approaches 1 minus 1, and that's going to be our solution. But just know, because the determinant 0, we have an infinite number of solutions. And so 2 and negative 2 is also a solution. Pi, negative pi is a solution. Just any number s and any number negative s. So if x is s and y is negative s, that's a solution. And so our u is in the form of x and y, and we can see that x is any value s, and y is just the negative of that value that we chose. So factor out the s, and we have this, you know what I mean? Our eigenvector is going to be s times 1, negative 1. Hell yeah. Where s is any number besides 0. And we did it. So that is kind of cool, because sometimes I mess up these linearly dependent systems in figuring out like what value goes where. But this is one technique, and I think it's tried and true. I haven't tested it for everything, you know what I mean? So there's no official proof here. But if you make your determinant just, you know what I mean, just a kind of a positive bump, I think if you make your determinant a positive bump, and then take your 0 value and bump all these values, whether it's x, y, z, or whatever, just by that same bump, I think you can approach the answer every time. So hell yeah. So that was definitely the fast solution, but that still was hella slow. And now, this video is interesting. I just kind of grinded it out, and I was happy too. So you can just kind of watch the rest of the video. But this is what we did. We wanted to get a solution a, x, b. We needed to find the inverse of a, so we modified our, a that didn't have a determinant. And then we modified our 0 vector as well. So hell yeah, and then we got a solution. Alright, thanks for joining me. Booyah! Alright, hell yeah. So we have linear algebra, and we're going to do eigenvalues today. And we're going to do actually something pretty cool. We're going to do something where in mathematics, if you get something where you're dividing by 0, maybe it blows up. And what you can do is, instead of dividing by 0, divide like by 0.1 or divide by 0.01. And so, and then you might get an answer that's, kind of approximating what's happening there. So that's what we're going to do, and it's kind of interesting, and it's just an exploration of solving a linear system using this. Because prior to the chapters with eigenvalues, and that's literally like one of the last chapters in here, we got done taking matrix A and multiplying it by a vector of solutions. And that's going to, so AX is equal to B. B is your vector of constants. And so how would we solve something like this? Well, we're going to multiply both sides by the inverse of A. This becomes the identity matrix. The identity matrix times any matrix is just itself. So we get just the matrix of solutions on this side. And then on this side we have the inverse of A, which is a matrix. And then we have the vector of coefficients, which is a matrix. So all we have to do is just multiply two matrices together, and we get our solution. Now, what we're going to do is we're actually going to do this, but the issue we're going to run into is that this has to, the determinant of this, to find the inverse of a matrix. So if I have the inverse of matrix A, the equation for that is 1 divided by the determinant of matrix A. And now here's where you can see if the determinant is 0, we're dividing by a 0. Cool. And this is also times the adjoint of A. And the adjoint of A is just the cofactor transformed of A. And hell yeah, and we'll get into this sec. But just the fact that we're dividing by 0, our whole method is just to be like, well, let's change our values just a little bit. And then so this determinant's not 0. Maybe it's just like, 0.1. And maybe that's good enough to get an estimate. So that's what we're going to do. And we're going to, start with the proof of, how to work. I guess what we're interested in is first, well, this is my first go, but we're going to solve for this scalar. Because what are we doing? So it says determine eigenvalues and the corresponding eigenvectors of matrix A. And so we're going to say matrix A, and if this is matrix A, if multiplied by U, so this would be your xy, so U is probably going to be in the form of xy. Well, it is, so that's going to be, so if I have AU, that's the same thing as 2x plus 0y might equal something we just don't know yet. So it's just that side of the equation. And then we have 1x plus 3y is equal to, something. Okay, hell yeah. Oh yeah, and this is really fascinating to me. Oh yeah, and I've never even done this. They didn't even do this in the book. Where it's just like now I have this scalar multiplied by xy. So this side of the equation is literally just going to be, we'll have to think about this one. Alright, I don't know if I'm 100% sure, but this should just be scalar x times scalar y. They really didn't go over that part. And that's the thing with, risking, being a little bit risky, making videos when you're just like, hey, we just went over this and now we're going to try to teach it. Okay, hell yeah, but this is the main meat. Is that we're going to derive, I guess, how we're going to actually find some of these values. So the first part of this derivation is kind of interesting, but it makes sense. Like right here we have matrix A, and now this scalar, I would put in like parentheses like this. It is not a matrix, it is just a scalar. It's like the number 2. It would be like having, if I wanted to multiply matrix A by 2, I would just have 2 out here, and I would just multiply all numbers by 2. There's no matrix multiplication going on there. So what we need to do is turn this scalar into, and I don't even know if what I just said was even true. Whoa, they did not cover this in the textbook. It's half true. It's kind of fascinating from like just reading textbooks. They're not giving you like every little piece. Because matrix U right here is an x, y, and then we just have some sort of scalar multiplied by xy. So if we multiplied this through, we would have, that scalar x and then that scalar y. But the proof says, hey, we want to get this to the other side. So not only, and we want to subtract, what do we want to do? We want to, we're going to actually subtract this whole quantity to the other side. Alright, yeah, no, I'm glad I'm taking a risk on this. Okay, cool. Okay, yeah. Because I was thinking, well, this scalar just gets multiplied, but let's take it to the other side first and then talk about it. So we have this, and let's maybe grab a new sheet of paper. Hell yeah. So we have matrix A times vector U is equal to scalar, which is the eigenvalue. The scalar represents the eigenvalue, and times matrix U. Hell yeah. And then U is the eigenvector. So there we go. So we're going to find the solution for xy. We're going to get U, and we're actually going to get values in there. So that's our goal, is to actually get numbers in those locations and a number for this eigenvalue and for this eigenvector. Hell yeah. It's my first rodeo, but we'll get to the cool part in a second. So sweet. So what we want to do is maybe subtract both sides. Just get this to the other side. So that's going to be AU minus this. And but now when we subtract this, what's going to happen? And this is the 0 vector. So we're still we still have this side. This would be a 2 by 2 matrix multiplied by a 2 by 1 matrix, resulting in a row 2 by 1. So this would result in a 2 by 1. 2 rows, 1 column. This side, I mean, if we just multiplied the scalar times the 2 by 2, this would result in a 2 by 2. So we're good to go there. But this next part is what kind of threw me for the loop here, and I'm kind of just learning on the fly. If I want to factor out, you know, that we both have this vector u, so I could do this, parentheses a minus the scalar times u. But this is where we would probably be wrong, because this is a 2 by 2, and this is a scalar. And so what we have to do is we have to just take the scalar and multiply it by the identity. And this is kind of cool. If you multiply by the identity, you can multiply it either side. Doesn't really matter. But we're going to do the identity of a 2 by 2 matrix, which just looks like that. So that's what we're going to do. We're going to take A minus this scalar times the identity. And you would have done that probably maybe at this step. You would say AU is equal to this times the identity of U. So now you have like, hey, this matrix right here is the same as that matrix. Now we can start, you know, adding and subtracting both sides of the equation. So we would subtract this from both sides of the equation. And hell yeah. And then we're just left with that 0 vector. And hell yeah, you're just left with this. Okay, so that's going to be the first huge part of the proof. The second biggest part of the proof is the fact that we have kind of a multiplication of two things. So this comes up a lot in algebra, where we have, and this is the 0 vector, so just keep that in mind. It's 0, 0 in the x and y values. The solution, not the solution vector, just the, what do you, I don't even, yeah, my terminology is a little bit bummed up. But anyway, so anytime that you have like, hey, I have like x plus 1 and then x minus 1 is equal to 0, well, you have like, hey, you have two products that if this is 0, this could be any number, and vice versa. If this was 0, then this can be any number. So then you have that. If they're both 0, cool, that equals 0 as well. That's the obvious solution. No, in this case, the obvious solution is just saying, hey, well, here's my vector xy. What if x is 0 and y is equal to 0? Then this thing is surely 0. But the proof says, hey, what if x and y could equal any number? You know what I mean? Or at least one of them is a number and maybe the other one's 0, or you know, vice versa. Just a combination where it's not, where just in general xy is not 0, 0. So not that specific combination where xy is not 0, 0. So then this side of the equation would have to be 0. Cool. Alright, hell yeah. This one's going to challenge me because I'm kind of new to these proofs. But what we have is that in this case, we do have, if x and y are 0, like that's a solution, because this side of the equation is the 0 vector, x and y can be 0. So x is equal to 0, y is equal to 0 is a solution. So I had to pause the camera and just choose, you know, a problem that I thought was linearly independent. Because this is not linearly independent if we can say there's some value here of this that forms another solution. Okay, and this makes sense to me. This says that if this matrix over here is, I think, equivalent to 0. I don't know how that that jives. I don't think it has to be, I don't think it has to be a matrix of all zeros. It just has to be linearly dependent, where when we, you know what I mean? Ah, damn it. I think if we set this equal to the 0 vector, I think that's how it works. Like, hey, we have this matrix, and if we set this matrix of values equal to 0, does that even make sense? Alright, not quite. We would have to multiply it by x and y, and then we have just this. This is a matrix. Multiplied by x and y is the 0 matrix. So we're just essentially solving this for the non-trivial solution. But, x and y is equal to 0, and maybe that is the only solution, and that's a unique solution. If that was a unique solution, this matrix would simplify to the identity matrix, and we're just a 2 by 2. So you have the identity matrix, and that's just going to equal, so we would have the identity matrix times x and y is equal to the 0 matrix. So this says that 1x is equal to 0. So we have 1x plus 0y is equal to 0. We have 0x plus 1y is equal to 0. And therefore we simplify to 1x is equal to 0, 1y is equal to 0, which is x is equal to 0, y is equal to 0. So that is... Yeah, I totally even forgot what we were talking about. That is a linearly independent system where the only solution is that if x is 0 and y is 0. You can't have any other combinations. You can't have 1x plus 1y at all because it's, well, damn it. Alright, hell yeah. Let's show this system of equations, which has, it's x plus y is equal to 2, and then you have x plus 2y is equal to 0. So you have something like this. The coefficients are 1, 1, 1, 2. You're going to multiply by x and y, and it's going to equal to 0. And then when we do row echelon form, I'm going to multiply the top row by -1, and then I'm going to take the bottom row and then, take the top row and add it to the bottom row. So I have -1 plus 1 is 0, -1 plus 2 is 1, and then we have, and this should be in, we would set this up like this, 1, 1, 1, 2, maybe augmented matrix form. And then so yeah, multiply by -1, and so we have -1 plus 1 is 0. -1 plus 2 is 1. -2 plus 0 is -2. So now we're left with this. I need to get this to be a 0. We want it in reduced row echelon form. So I'm going to multiply the bottom by -1 and then add it to the top row. So 0 times -1 is still 0. Added to the top row is still 1. -1 times 1 is -1. Added to the top row, this becomes 0. That's what we wanted. And then we have -1 times -2 is +2. Added to the top row becomes 4. So now our system becomes this, where we have, what did this, yeah, this stays the same. So we have x, this is our, we have 1x plus 0y is equal to 4. So you have x is equal to 4. And then we have 0 times x plus 1y is equal to -2. So we have 1y is equal to -2, or y is equal to -2. And from this, you can see that this is the linearly independent. We get reduced row echelon form. We don't get any row to have a 0, 0 in it. And if this is one solution for -2, and that's kind of interesting. Now I'm kind of like learning on the fly, is if I do have a unique solution that is not the 0 vector, for a linearly independent equation, you can't put in x is equal to 0, y is equal to 0. That is not a solution of a linearly independent I don't even know what you call this anymore, system of equations, if you have a unique solution that's not, if this is a unique solution that's not x is equal to 0, y is equal to 0, and it's linearly independent, x equals 0 and y is equal to 0 will not be a solution. And you can just see, if we throw 0 plus 0 does not equal 2. Now, this one does. 0 plus 2 times 0 equals 0, but one of the equations does not jive. Alright, hell yeah. And I'm always trying to find like the aha, or like the in the proofs, be like, where's the aha moment? Well, it must mean that this matrix is has more than one solution, because I mean that's what we're trying to find, and maybe it doesn't. Maybe we're just assuming it does, because the problem says, hey, it probably, if it's maybe fits into the category of eigenvalues and eigenvectors. When we do this portion, now this has an inverse. You know, I mean, we definitely have an inverse. This determinant of A is not going to be equal to 0. But what we're going to say is that this determinant is equal to 0. And maybe we just do that from a says-so perspective. And I think we do. I think we say, hey, we're just going to say that this matrix has a determinant that equals 0. So that's kind of what we do. So let's maybe throw some more juice. All right, hell yeah. So let's go through this. So we have matrix A times vector u, scalar times vector u. And I think it's good to not even use the word eigenvalues and eigenvectors until, I don't like when people's names get involved in physics. I honestly don't. You know what I mean? Until you've actually used them. Hey, this is just a matrix, this is just a vector, this is just a number that's a scalar that we're trying to find a value to. Cool. The first part is we're going to multiply this scalar times the identity matrix that's the same size as this matrix A. So now we can see that this is, you know, I mean, this is technically scalar times I. Which is scalar, for our case, it's going to look like that. And you can bring that now into the matrix, which is that. But you can't just put brackets around this and say this is a scalar. This is a matrix. No, this is a matrix, and that's multiplied by a scalar. So I guess you would do this. You know what I mean? To show that, hey, we have same size matrices. Okay, hell yeah. So now we're going to take this and subtract it from the other side. And so we have A u minus scalar identity u. Now I'm going to factor out, because u is common to, and this is the 0 vector. When we subtract, you know, we have matrix, this reduces to a 2 by 2. When you multiply this it reduces to a 2 by 1. The solution is a 2 by 1. This 2 by 2 multiplied by u, which is an xy, which is a 2 by 1. A times u is a 2 by 1 matrix, which is something that looks like that. Hell yeah. Okay, sweet. So we're going to factor that out. A minus the scalar I. U is equal to the 0 matrix. We're going to say that, yeah, we're going to identify that because this side is 0, which is different than that simple problem that we did. Why did this problem work out? Because we don't have the 0 matrix over here. You know what I mean? If we just have x plus 2y is equal to 0 and x plus y is equal to 0, hell yeah, we have you know what I mean? The solution to this can be x is equal to 0 and y is equal to 0. By definition of, like, you know what I mean? Because we don't have any, and that's where I forget my terms, but like, is this the homogeneous solution or something like that? But hell yeah, you know what I mean? The second you put a value here, then you're no longer have this x is equal to 0, y is equal to 0. It seems to be the case for that. But hell yeah, when this is equal to 0 on both sides, yeah, I can put 0 in x and 0 in y all day, and it's going to equal that. And then maybe I could throw in another value, you know what I mean? maybe I could, you know, throw in another value that works, you know, just equally just fine. I could throw in, yeah, so I have no idea. Okay, hell yeah, so now I'm kind of getting this proof. Like, this is going to reduce to a matrix. You know what I mean? This kind of is a matrix. I'm going to put kind of matrixy brackets around it. This is a matrix vector of solutions. So I can either say this matrix is equal to 0, like any, yeah, and I think that's an identity. Any matrix, matrix A, times the zero matrix, or, you know what I mean, 0 vector, is always 0. Is always going to be, I don't know, the 0 vector. Yeah, that's how you'd say it. Because, yeah, and that's how you would have to, I think even if you had a 2 by 2 matrix A with numbers in it, multiplied by a 2 by 2 matrix with all zeros, that would still equal, everything would equal 0. So it doesn't matter if this is a vector or just 2 matrices, and I'm not too skilled on that. You know what I mean? Can this 0 vector, I've heard it be called a 0 vector, can it also be just a matrix filled with zeros? I have no idea, but it's similar. It's going to be similar. If you got zeros everywhere, you're just going to get big zeros. It's up to making sure these matrices multiply where you can actually multiply them, where the rows on this side equal the columns, where the columns on this side equal the rows on that side. Okay, so we have 2 different types of matrices, so it's still back to very similar. It's like, hey, if this side is 0, we're chill. You know what I mean? Because I think that is one of the proofs that the textbooks actually don't go over. And actually, I'm really liking this video because you know, even if will never make a video on this topic again, and I'll just move on to the next topic, it really shows you like the struggle. The struggle is always real. And you're going to be looking through the textbook proofs, and they're just going to go from one step to the next, and a whole semester worth of college education could be from one step to the next. Kind of, you know what I mean? It might be 3 days of classes going over, like, you know, this concept maybe. But hell yeah. And that's just, I don't need to stutter too much. We can work on that. So, cool. So we have that this side could be 0, this side could be a matrix full of zeros, and this side could be the 0 vector. That's kind of what I'm going to say. Matrix full of zeros and a 0 vector. I have no idea if that's exactly how you would say that. But they could either both be zeros, or if this one's 0, this can be any number. We just kind of showed that because our solution... Sorry, this is the solution vector. This is the vector of constants. Yeah, if the vector of constants over here, and that makes sense because these are constants, and yeah, if our constants are 0, vector of constants are 0, x and y is equal to 0 is always a solution, which is the 0 vector. If I'm saying vector u is x and y, then the 0 vector is 0, 0 in those x and y locations. So, yeah, I'm starting to pick up kind of the method of things. And we're just going to totally run out of juice. Alright, we'll see how much we can do before the camera burns up. Alright, so I think I am thoroughly satisfied that this side is the 0. If this is equal to the 0 vector, hell yeah, it's 0. And why? Because it's this could be linearly independent. So one system says if this matrix, yeah, I think that's the deal. If this matrix is linearly independent and can reduce to, you know what I mean, the identity matrix. Because when you augment this matrix, I'm just going to call it A star, and the 0 for zeros for the coefficient vector over there. When we do reduced row echelon form, you're going to get, and we're only having a 2 by 2, but you're going to get this. And you're going to say that x is equal to 0 and y is equal to 0. So yes, if this is linearly independent, that's the solution. What we're going to say is if and And, oh, and you don't even need to do that. I think we proved that this doesn't even have to be linearly this could be linearly dependent. I could have x plus 2y and then 2x plus 4y. This is a system of two equations that are linearly dependent, not independent, and still x is equal to 0 and y is equal to 0 is a solution. The only thing that makes x equals 0... Alright, hell yeah, so we're back. So, yeah, the only thing that makes x equals 0 and y is equal to 0, I think it's just the fact that the constants, the coefficient, the matrix of coefficients, or the vector, it's the vector on that side, the vector of coefficients, b, is 0, 0. If b is 0, 0 on this side, or the 0 vector, then x is equal to 0 and y is equal to 0 is always a solution, regardless of whether this is independent or not independent. And we just showed that if this matrix is linearly independent, where the determinant of A is non-zero, you know what I mean, some sort of value, then this is a linearly independent, and do you even say a matrix is linearly independent? The system of equations, the system of equations as written is linearly independent. If this matrix has a determinant that's a known value that's not 0. If that determinant is not 0, then you have a check on reality that this is linearly independent system of equations that has a singular solution. Because it's equal to the 0 vector, that solution is 0, 0. Half the battle is actually just talking your way through this. I mean, it would be the same thing as like 2 plus 3 is equal to 5, because 2 is 1 plus 1, and 3 is 2 plus 1, or 1 plus 1 plus 1. You know what I mean? I mean, it's the same type of like mathematical logic, where you're still just trying to figure out how things work and operate, and trying to say them in correct ways. Now, even just the fact that you have a matrix and then a vector, if you have a vector is equal to a vector, you can only, you know what I mean, we're equating vectors. What's in front of the vector is a transformation, you know what I mean? So I always think of, and that's from the literature, is like if I have ax, then I'm transforming this vector. I'm taking vector x and I'm transforming it by matrix A. So it's a matrix, it's a vector transformation. So if I consider a vector just to be 2 points, you know what I mean, there and there, or the location of a point with 2 x and y coordinates, then the transformation will rotate that, or rotate and lengthen, you know what I mean, with those properties. So it can, or keep it the same. It can either keep it the same, or it can rotate and lengthen. It's still, and is that all true? Will it still be a point with 2? Is there any transformation where you actually, yeah, and that's where it's just like, I actually studied this pretty fast, but it's just fascinating to ask yourself questions. Just like, well, isn't there a transformation where if you start with a 2 by 2, like you can have a matrix where you multiply, and if your matrix is not linearly independent, if your matrix is linearly independent, hell yeah, you're going to get a rotation. Yeah, so that's I don't need to stutter so much. If we have a matrix that's linearly independent, this will be a rotation and a change in length of that point, or it'll stay the same. It'll be a transformation. If matrix A is the identity matrix, which is by definition a linearly independent matrix, where the determinant is non-zero, and the identity matrix just returns the original matrix, so we have no transformation. I'm actually really enjoying this video right now, because this is something that I don't think I would ever do as a college person. You know what I mean? Just being like, hey, I'm just going to talk my way through what I just learned. Because it's heady as hell. Maybe you can follow the numbers. When it's like 2 times 2 is equal to 4, you know, whatever variable it is, you can follow along with that. Why are you multiplying those numbers? That might be, you know what I mean, you'll never know. You know what I mean? So it's very good to talk your way through concepts to see where your gaps are. And even just with this video, I found like 4 little things between an independent system of equations and even just saying it's a system of equations. I was just going to call them random A numbers. You know what I mean? All right, hell yeah. So I think we're doing pretty good. So we have a transformation on a vector. If this transformation is linearly independent, it will change that point or keep it the same and change its length or keep it the same, but you'll have a rotation and a change in length. If it's dependent, who knows? You know, all bets are off because it depends on how many variables you have in that vector, and you might just be left with a scalar. And yeah, I don't know. Where like here's one of the solutions. I don't know, like x is 0 and y can be any number. Well, if x is 0, does that even account for a dimension? You know, is the range just one dimension? You know what I mean? Where if you have 2 points, this point is an xy coordinate. If the x coordinate doesn't really matter no more, and then this point is just described as somewhere along the y-axis, then it's then the x coordinate's actually irrelevant. Even though the x coordinate could be said it's to be 0, I think that's where it gets to be linearly dependent. Where it's not... well, I don't like the use of independent and dependent. I feel like I don't even know what they mean no more. Alright, so the whole idea is that if this is linearly dependent, what do we know about matrices that are linearly dependent? They don't have an inverse. And why? Is because the inverse of a matrix is the 1 divided by the determinant of the matrix times the cofactor transformed of that matrix. But mainly is because the determinant will be 0. And so if the determinant of this matrix is 0, then we have a linearly, I don't even want to write it, but a linearly dependent matrix. And if we do have that, we have a not just a singular solution, we have an infinite number of solutions. Cool. And so we are guaranteed to get a vector of solutions to look in this form, where S can be any number. You know what I mean? So we're going to get x is equal to 1, and x is equal to -1. Or x is equal to 2. This could be 2 and -2, 3 and -3. They'll throw in pi and -pi. So that's going to be the deal there. This one is going to be different because it's not a function of x. X is just 0. And it's going to be, and then y can be any value, any real number, and it's going to satisfy that equation. And I think that's where they would call the range on this a range of 1, or the range is just any real number where y is any real number, And I'll have to go back to that, but yeah, you lose a dimension. Here you lose a dimension, here you keep the xy dimension, and but there is a relationship between x and y. If one is a number, the other is just the negative of that number. Some of the linearly dependent equations are, you would put s and t here, where x could be any number, and then actually y could be any number. Alright, hell yeah. So this is so interesting because I thought I was just going to breeze through this, get to this part, because what we're going to do, which is kind of fascinating, is we're going to say, hey, this isn't equal to 0. We're going to say it's approximately 0, and we're going to make this determinant, you know, approximately 0. And then if this determinant is approximately 0, this part of the equation will jive. You know what I mean? It's not going to blow up. 1 divided by 0 goes to infinity, where 1 divided by 0.1, let's say we get a determinant that's 0.1, we're going to say that's pretty close to 0. Then this just goes to 10. So we're going to have 10 times the cofactor transformed of that matrix, and then we're going to use that. It's going to be the inverse. So at the end of the day, we're going to find an inverse to this matrix. And what's the overall form? We have this times u is equal to 0. And so I before my camera just totally dies, I will, this is what we're doing in this video. We have this matrix. And just know that this is a matrix. Once we do the subtraction, it's still a matrix. We have this vector of solutions is equal to the 0 vector. We're going to take the inverse matrix on both sides. So this multiplied by that, and then the inverse on both sides, multiplied by the 0 vector. So when we do this times the 0 vector, we still get the 0 vector. Oh no, is that even going to work? Oh yeah, and then duh. So, and again, this is such a weird one, but it does work. So it's kind of interesting. We can't multiply by the 0 vector because we just proved that any time times 0 is just going to be 0. So now we're going to take the 0 vector. If we said the determinant was like 0.1, we're just going to crank these values to 0.1 and 0.1. The only tricky thing about this is I only want to change one value, because this matrix could be a 3 by 3. And if it's a 3 by 3 and it has a bunch of zeros in it, and I change 3 rows, by 0.1, 0.1, because the determinant is a multiplication process, you're going to get 0.001, and you would have to have, and then 1 to... So that would be your determinant. Your determinant would be this, and then 1 divided by it would be 1,000. Or if you just take one of these rows and do a 0.1, or just do the simplest operation that gains you a 0.1, where your determinant just is a 0.1. It could be either negative 0.1 or positive 0.1. I don't think it really matters. But, and you might have to put a 0.1 somewhere. You might have to put a negative 0.1 somewhere. But I think my goal is to get a positive 0.1 on the determinant, and then change these to a positive 0.1. And I haven't done this for all problems, but I think it will work out in all solutions. I mean, I don't have a proof for it. I just tried it in 3 different problems, and it seemed to work. So that's what we're going to do. So that was hella slow roll just to get to what are we doing? We're taking this, where this for sure does not have an inverse, because the determinant's 0. We're going to say the determinant's at least 0.1, close enough to 0. And then we're going to take the inverse of both sides. So then our solution, where we have u is equal to this matrix that we modified just by a little bit, multiplied by the 0 vector, which we now modified. So I'm going to call this star, and maybe I'll call this star. A modification of this vector just by a little bit, and a modification of this just by a little bit. The analogy of this, I got 2 minutes. The analogy of this is take the integral of 1 divided by x dx. Simple. Cool. So we're going to say this is the integral of x to the negative 1 dx. Well, we're going to say this is the integral of x to the negative 0.9. I think that's the way I kind of like to do it, maybe. Dx. So all I did was just change it by a little bit, and now we have x. Now the integral is going to be x to the negative 0.9 plus 1 divided by negative 0.9 plus 1 plus a constant. So the natural, and this would be the natural log. So we have x to the 0.1 divided by 0.1 plus c. Now we're going to have a 10 here, so we have 10x to the 0.1 power plus c. And I think c here has to be like a negative 10, positive 10 to make it work. But that is the natural log. And that's just such a, I don't know, maybe a more, visual approach. Like you might be able to follow the numbers and graph the numbers and add up the areas when you do the integration process than just doing some sort of I can't divide by infinity and then coming up with a strange, symbol and doing it that way. So that is the analogy of what we're doing. Change the determinant by just a little bit, and then we're going to change the zero vector just by a little bit. But thank goodness I went through that whole, grind just so I'm actually saying correct usage of the terms. So hell yeah, I'm going to take a little break. We'll come back and do this one. Alright, hell yeah, let's see if we can bust this out. So we have matrix A times U is equal to the scalar times U. I'm going to do matrix A times U is equal to the scalar times the identity matrix that's the same size as matrix A times U. I'm going to take this and subtract it on both sides of the equation. So I'm left with the zero vector over here. And then I have AU minus the scalar times the identity matrix times vector U. I'm going to factor out vector U. So I'm going to have A minus the scalar, identity, and then we have U. Since this is a coefficient of constants that's 0, it doesn't matter whether this matrix is linearly dependent or independent. X is equal to 0, and then this vector is in the form xy. X is equal to 0 and y is equal to 0 is a solution. If it has another solution, then we know it's linearly dependent. It doesn't just have a unique solution, it has an infinite number of solutions. That will happen if this matrix, if the determinant is 0. And so, yeah, it's fascinating because we at least need to go down that route. And so we need to, we do need to do that route. So what we're going to do is we're going to solve this, and we're going to find its determinant is equal to, so I'm going to do the determinant of this matrix is equal to 0, and I'm going to solve for this scalar. Because the determinant of a matrix is just a scalar number, and so we're going to say that's equal to 0. Cool. Alright, so let's do that. So matrix A is 2, 0, 1, 3 minus the scalar times the identity matrix. Hell yeah, so that's what we have so far. And this is going to be equal to, sorry about this. We have the determinant of this. We're kind of doing two steps at once, but this is equal to 0. So we have to, this can just get foiled in to where this, I'll do it aside. This is just the scalar. So that's a very simple matrix operation. Just taking the scalar and multiplying it through the matrix. Man, and I almost forgot. It's like, yeah, a scalar multiplies every value of the matrix. I think, you know what I mean? That's crazy where I'm just not 100% on that. But that's good. It's good to be like in doubt because you're just like, well, I can't prove it, so therefore I'm just assuming. And then, okay, now we're going to move on. So if we have these matrix, we're going to take this, subtract that. So we're going to have the determinant of 2 minus the scalar. And see, I'm just calling this a scalar. I think it's way better than calling it lambda. I hate Greek letters and their verbiage. And then also calling it the eigenvalue. But this is the eigenvalue. It's lambda. It's just a scalar. Cool. And then so we have 2 minus the scalar. We have 0 minus 0. We have 1 minus 0. And then we have 3 minus that scalar. Now we simply find the determinant of this side. The determinant of the 2 by 2 matrix is just going to be the diagonals multiplied minus these diagonals. Those diagonals are 0, so it's just these diagonals multiplied. And we're left with kind of one of the simpler eigenvalue problems. So now the scalar can either be a 2, so scalar 1 can be 2, or the second scalar can be 3. Both satisfy these equations. It's the classic, I have a product of two terms equals 0. One could be 0, the other could be a number, vice versa. They both could be 0. You know what I mean? So we have, this could be 2, This one could be 3. Well, and in this case, they can't be both, because we're just saying, hey, this is the, got to catch myself when I stutter. This is the same, yeah, this is like 2 minus x, 3 minus x. If I'm claiming x is equal to 2, x can't be 2 and something else. Cool. All right, so now we're going to do this. This is when that scalar is going to be 2. The first scalar is equal to 2. The first eigenvalue is equal to 2. Now let's find the eigenvector. You know what I mean? And I think the second you say eigenvalue, eigenvector, it's like one extra step that just confuses my brain. It's like I don't need to put names on things that actually don't identify. Like down the road, sure, when we're talking about eigenvalues, maybe that means something. But currently, it means nothing. So I just want to see what dimensionally things are. This is just a vector. That was just a scalar. Cool. And then so now what do we do? Oh, we're going to plug this value back into our matrix. This matrix, I mean, we took the determinant of the matrix, but this part right here is that matrix. So we're going to have 2 minus 2. So I'm going to say this matrix is 2 minus 2, it's 0. We're going to have 0. We're going to have 1. And we're going to have 3 minus 2 is 1. So now this is our matrix. And this is where it was like even starting this video was kind of pointless, but it had a lot of benefits because I struggle at talking my way through this. And I'm sure maybe people that would watch this also struggle through. And so I think we did a good job of like pointing out maybe where those struggles were. And I think it is good to cast doubt, because then you watching can be like, oh, I totally know that he's struggling and I can see above that. I think that's the coolest thing. Like when you're just like, oh, I get this more than this person does. And that's really good, because then you can find ways to teach it better, more efficiently. Now, this is just a very simple indeterminate system of equations. But now we're going to do kind of the weird thing, is that we're going to make sure our determinant, so if I did the determinant of, I'm just going to do d of that, is going to be 0, because we have 0 times 1 minus 1 times 0. So what I'm just going to do is just change one value. And I want it to be a positive 0.1. So I'm just going to, I'm going to change this value right here to a 0.1. And when I do that, I'm going to change this 0 vector into 0.1, 0.1. Now, I don't know if this works all the time. I think it works as long as you choose this determinant to change one value where you can make it a positive 0.1 change. And you can even refine. Alright, hell yeah, another battery in. Sweet. But hell yeah. And you can even refine your answer by changing this to 0.01. Some answers need refining, or will be off by a certain factor. Some will just actually get you the right answer right away. So hell yeah. So now what we're going to do is that this is our matrix. It's slightly changed. That's all we're saying is like, hey, if I slightly change a matrix, how... You know what I mean? Like that is the general gist of this. It's just like, hey, I slightly changed it. How off could it be? And that's what we did for, this integration. If I have 1 divided by x, well, can't that just be like 1 divided by x to the 0.9? You know what I mean? How, aren't those very similar? This is just 1 divided by x to the 1. This is 1 divided by x to the 0.9. I could put another 0.99, and then you're just like, whoa, they're very similar. And then so aren't they actually going to follow natural log of x plus a constant? Pretty close. And hell yeah, they will. Maybe just for a short bit, but maybe that's all you need. Okay, so hell yeah. I think we're ready to do the juice, and I think I'm about done with this. Okay, so what's the inverse of a matrix? It's going to be 1 divided by the determinant times the adjoint of that matrix, which the adjoint is the cofactor transformed. So the determinant of this is negative, or 0.1 times 1 minus 0. So we have the determinant So the determinant is 0.1. 1 divided by the determinant is 10. So right here, for the inverse of this matrix, we're going to have 10 times the adjoint. The adjoint is the cofactor transformed. The cofactor transformed is the minor with a positive negative sign change. And so if I'm in the row 1, if this is row i's and this is row j's, negative 1 times I plus j times the minor is the cofactor. And so if I'm at the location row 1, column 1, 1 plus 1 is 2, negative 1 to the 2 is a positive. This one is row 2, column 2, 2 plus 2 is 4, it's even, it's also positive. These are your negative ones. Row 2, column 1, this is 2 plus 1 is equal to 3, that's negative, we get that negative. This is row 1, column 2, same thing, negative. Hell yeah. And I think it's kind of difficult to take minors of a 2 by 2. I had to look that one up. I'm going to take the minor of this location, and it's going to be no sign change, so that's the cofactor of this location. The cofactor transformed is this reflected along this diagonal. You know what I mean? So if I actually did the cofactor of this matrix, I would write 0.10. So I'd take this and write it down, and I would take this and then write it down. What we just did was we kept the diagonals the same, and then we reflected anything on this side of the diagonal that way. And that's all it is. So for this one, we're just going to use the visual of reflection. So I'm going to do the diagonals first because there is no reflection. The minor of this location is taking this value and crossing off the column and row and finding the determinant of the remaining matrix. It's a 1 by 1 matrix, and who knew if you just have a 1 by 1, the determinant is that number. So sweet. The minor of this location, cross these out, is the determinant of the remainder. So the minor is 1 at this location. The cofactor means that there's no sign change at that location. The transform, and it's not reflipping because it is on that diagonal. So I just have 1, which is the minor. So let's go a little faster. The minor of this location, cross out those, is 0.1, no sign change, no flip. The minor of this location, cross out those, is 1. There is a sign change, negative 1, and the cofactor is a flip. So that's going to be a negative 1 in this location. The minor of this location, cross out column and row. The determinant of the remainder is 0. We are going to have a sign change. That's going to be negative 0, but it's just still 0. And then we do flip it. So the minor at this location, or the cofactor at this location transformed is up here, 0. And now we have 10, 0, negative 10, 1. And so this is our inverse. So A inverse is that. Let's see if we can drive this out. We got 5 minutes, and that's all I want to do. So now, like, this is a system of equations. AX is equal to B. We just found inverse of A, so we can say that X is equal to inverse AB. So here's our matrices and our vectors. You know what I mean? But they're all matrix. I can put the matrix thing around everything, but these are your vectors. So hell yeah. So I have the matrix of solutions is just this times the solution vector, which we said was the 0 vector, but changed a little bit just by that same value, that same, you know what I mean, nudge of 0.1. And this is a hell of a lot more work than just doing it the other way around. And we're going to be done once we get, you can do it for the other value, the eigenvalue of 3, the same way. You can use my process and you'll still get that. So hell yeah. So we're going to have, so to find our vector of solutions, which is x and y, is going to be equal to these two equations, 0.1, 0.1, and I'm just going to write the solution right here. So we're going to have, so and if I do this, so in this spot right here, first row, first column, 10 times negative 1 plus 0 times 0.1. So that's going to be 1 right there. And then how about this part? It's going to be second row, first column. Negative 10 times 0.1 is negative 1. And then we have plus 0.1. So we have negative 1 plus 0.1. So this is one of those cases where it's approaching, you know what I mean? So we still have negative 1 plus 0.1, we have negative 0.9. But if we change this to a 0.0 and 0.0, and then we did it for our determinant where this is 100 and 100, and then this would be point, then this would be point, that would be that, and this would be 100. We still would have 1, 2, this would still be 1, and then we would get 100 times this, and we would get our 1 because we would change that. So this first value would still be 1, and this value would be negative 1 plus 0.01. So that would be 0.99. So this would be or negative 1 plus negative 1 plus 0.01, which is negative 0.99. There you go, negative that. And hell yeah, you can see that the solution is approaching 1 negative 0.99. Now we just have to know that we know the determinant 0, so we know that this is like one solution of an infinite number of solutions. And so we have it in the form that our solution vector is xy this is it's approaching 1 negative 1, and we know it's an infinite number. It could also be 2 negative 2, and so we're going to say it is s negative s, and then we can factor out the s, and we can say it's s1 to the negative 1. And so that is how they get this vector u is s negative s, factor out the s is 1 negative 1, and then 1 negative 1 is one of the simplest eigenvectors, and I think that's important too. So hell yeah. I guess so. Whoa. Yeah, yep. Where the hell does this scalar come in? I think we should actually, that is one of the things that people never do. Alright, so we got some more juice on the clock. The thing that people never do is they never do this. They say this is matrix. No, they say this is matrix A. So what were we doing? We're taking matrix A times our solution vector is the scalar times the solution vector. So now we're going to test the waters. And we can use any solution. We can use 1 negative 1. That's just the simplest. Yeah, so that's where we can put it in. Our scalar doesn't change. Our scalar is still 2, but we can put anything over there. So let's try the simplest. We're going to do 2, 0, 1, 3, and then that's our vector, and then we're going to do 1 negative 1 is equal to the scalar 2 times 1 negative 1. We'll do the scalar part first. That's just going to be 2 negative 2, pretty simple. And then over here, a 2 by 2 times a, if we have 2 rows, our output's going to be 2. These are our, what drive the equation. This is like 2x plus 0y. These rows are associated with that. It's the dot product, and I need to say that more. Vector matrix multiplication is the dot product. That's all I know, just because I watched a black pen, red pen yesterday. And that's what, you know what I mean. But anyway, so you have this row, this column, so we have 2 times 0 plus 0 times negative 1, so we have 2. This row, this column is this value, so we have 1 times 1 minus 3 times negative 1. I'm sorry, 1 times 1, it's a dot product, so you're just adding. You're multiplying and then adding to the next multiple. So we're going here and then there. 1 times 1 is 1 plus 3 times negative 1. So that's 1 minus 3. That's negative 2. And hell yeah, those are the same. So anyway, so I thought that was just very interesting to take something where the determinant was 0 and it was being and you were trying to find a solution vector when your solutions were 0, and changing it so this determinant was just off by a little bit, 0.1 or 0.01, and this 0 vector was off by just a little bit, 0.1 or 0.01 as your solution, xy. And you can get the same, and I just think it feels more intuitive, even though I have no idea, you know what I mean, what's going on. I mean, not necessarily no idea, but it's similar to this. Like, I honestly can't, I'm not going to plot all the points. I don't even know what 1 divided by x to the 0.9 is. But it just feels more natural because it's a natural process. And it's a continuation of something that we've already done to get that answer. You know what I mean? Instead of just running into a hiccup where we can't divide by 0. This thing doesn't have an inverse because the definition of an inverse was something that's 1 divided by the determinant times the adjoint. And so we have to just come up with some new strategy. But this kind of shows you it's like a continuation process. Alright, hell yeah. That was super rough. But some of my roughest videos, like, are some of my best moments, I think. Hell yeah. Thanks for joining me. Booyah.